A very good afternoon, friends. Today we are going to discuss about understanding backpropagation and gradient descent. So welcome all. My name is Anashri Meshra. Today I will be your host and I will dive you deeply into two critical algorithms in machine learning, which is backpropagation and gradient descent. We will explore each steps in depth, helping you gain a thorough understanding of how neural network adjusts its internal parameters. So firstly, we will understand about what is neural network. A neural network consists of interconnected nodes called as neurons, which is organized within these layers. Each neuron processes input by computing a weighted sum and applying an activation function within this. Okay. So when we are going a forward pass, within this forward pass, there is two function that is happening. First is our integration, wherein we will do a weighted sum, and second is our activation. So we will discuss about first integration. So integration, within this integration, what we are doing? Add all the inputs like x1, x2, x3, x4. Say this is our input. And along with that, we will have four weights associated with this inputs. Consider these are the four weights associated with this inputs. What we are doing here is we will do the dot product of this and we will add one bias towards this that is called as our integration. Integration. Within this integration, what will happen? We will do a dot product of input with the weights. Dot product of input with the weights and summation of all these inputs with respect to their weights. Okay, summation of all the inputs along with the dot products. So here we will have W1, X1, W2, X2, W3, X3, W4, X4. Likewise, here we will have this plus what will be there? Plus bias will be there. One bias will be there. Okay. Then there is next term called activation. What will happen within this activation? Within this activation, my pen introduced non-linearity in the network. So here, say we will have activation functions like tangent activation function. Okay. So what they do with respect to sigmoid activation function, we'll have a formula. Here we will get the value of z. Okay, after doing the dot product of this, we will get a value called as z. Okay, this is called as integration function. There are two functions in between this. Okay, wherever we are doing a forward pass, we will have all the inputs and the weights associated with this. Along with other, it will go further, and at last we will have integration function and activation functions. What will happen in the integration function? We will do a dot product of the weights with respect to input. Dot product of weights with respect to inputs and plus one bias will be there. Okay, after getting this, within this activation function, we will have binary classification problems. Okay, as you all know, within that power minus z. Okay, and in the ReLU activation function, which is a rectified linear unit, likewise, in the tangent activation function, we will have a range of -1 till +1. That is tangent activation function. We generally use either ReLU activation function within the model itself, and at the end, whenever we want to classify the model into some binary classification, we will use a sigmoid activation function altogether. Okay, so after getting this integration function and the activation function, we will have our loss function. We will have our loss function. So here in the loss function or error calculation, we will take all the, we know how we'll calculate the loss function or the error calculation. So we will get the predicted value, whatever the predicted value, minus whatever the actual value is. So predicted minus actual value will give us the loss function. What we want this loss function. We want this loss function to be lesser. We want this loss function to be lesser. So for that, we will go backward. We will have a back propagation. Within this back propagation, we will have how we are going to update the weights. What we are doing for updating the weights? There is one thing called a chain rule application. Chain rule application. So here, what will happen? For example, if you have your weights, suppose from here, you are going back propagating here till here. Okay. So here, how the weights will be updated? So weight, whatever the weight new will be there. Weight new will be equals to weight old minus weight old del of W. This will be your what? Your updating weight or new weight will be there. New weight will be associated with this. Okay. Once you will go reach here, again, this new weight will be there. Okay. So W of new will be equals to what? W of new is equals to W of old. Whatever the old weight was, and within that old weight, what we are doing? We are just subtracting the learning as the learning rate. We are subtracting this eta value with this differentiation, partial differentiation with the, which was the old weight. Del of loss or del of your old weight. Okay. Del of loss to that of del of old. So this weight will be associated to this. This weight again go forward, it will be associated to this. Again, it will go here. Again, it will update this. Again, this is how we will have our, again, we will go forward. Forward pass we will do. Again, we will do the activation function and the what we can say integration function. Both we will do. After doing this, we will have again a prediction value. Within this prediction value, we will have what? We will have a loss function and the on till we will get the loss function very less or very minute. Okay, we want this loss function function to be minimum. So how it can happen? So whenever our predicted value and the actual value, the difference between these two values will be lesser, at that time our loss function or a cost function will be learning rate. So how learning rate is important? Okay, so learning rate during the gradient descent. What is in the gradient descent? I will tell you. Okay, if for example, if the learning rate, if we are taking a learning rate too high or more value we are taking, so the model may overshoot the minima, or what we can say, it will fail to converge here or reach a global minima. If it is too, if it is itself here and so it will never going to reach local minima. So we have to make this learning rate properly. So proper tuning of learning rate is crucial for efficient, and value is we are subtracting the old weight with the eta value to that of the partial derivative. So what is the new term here? When we are doing the updating the weights and about gradient descent. So what is gradient descent? Losses. Iteratively updating the network weights. Okay, iteratively updating the network weights. So, three terms. First is our batch gradient descent. Second is a stochastic gradient descent. And third is a mini batch gradient descent. So, batch gradient descent will do what? It will use the entire data set. It will use the entire database, okay, entire data set to calculate and give you the grade. It will take huge time, okay. And what is then the stochastic gradient descent? Stochastic gradient descent will update the point. For one point, it will update the weight. For one point, it will update the weight. Likewise, there is one more term called as mini batch gradient descent. So mini batch gradient descent will balance all this two, batch gradient descent and stochastic gradient descent. It will have a sets of data we will send into the neural network, and then it will classify. Okay. So there are again other optimization techniques also present, just, like momentum, which will accelerate a gradient descent and reduce the oscillation within the neural network. Okay, and there is AdaGrade, RMS prop, ADAM. These are all the adaptive methods which will actually to optimize the convergence. What we want to converge. It should reach a global minima. It should not going to reach the global minima. Okay, so this is very important. Then there are different terms called as data pre-processing and hyperparameter tuning. Data undergoes pre-processing, like outlier removal, feature scaling, selection, and hyperparameter. Like we will do hyperparameter. Within that hyperparameter, we will have learning rate, path sizes, epochs, how epochs will have dropout, early stop, batch normalization, which will use to prevent the overfitting of the model. Then there are in data augmentation techniques. We can have different data augmentations like translation, rotation, scaling, flipping, enhancing the model robustness, and generalization, the model. generalization the model. This is how we will understand, like after going through all this network and having this loss function or cost function lesser, these are all the techniques which will help us to have this loss or cost function to reduce this and the accuracy to be higher. Accuracy will be higher when the difference between the predicted and the actual value will be lesser. Okay. So if it is lesser, that means accuracy will be more. Okay. So this will be the helping out things like optimization techniques, regularization techniques. Okay. So likewise, there will be a model evaluation. How we are going to evaluate the model based on that. So we will have, if we will have a classification problem, okay, we can use it by confusion matrix, accuracy, precision, recall, F1 score likewise. And if we are having a regression problems, the activation function. And when it comes to binary classification, as we all know, when it comes to binary classification, we will going to use a activation function. Or when it comes to more than two variables, when the categories are, when the class can use a softmax activation function. Okay. So this is how we will going to understand, this is how we can find out the model evaluations, the scene, the optimization techniques, regularization techniques, and again, we are updating the weights. Okay, so weights will be W new is equals to W of old minus eta of the old weight. Okay, so this is how we will get the loss. This is how we will update the weight. So after this, we will understand about our general flow. What we are doing first, we are having all the inputs. Then we are having all the integrations of this. We are applying, we are doing a dot product and summing a bias. That is what our integration function will do. Then at activation functions, we will use any of these activation functions and we will get the output according to that. Okay. Then we will find out the error calculations. Okay. Now this error calculation or a loss function or a cost function we want to be lesser. So for that, we will again backpropagate, again do a backward pass. Again, we will add, again, we will do an optimization techniques like we can have our mini batch gradient descent. Likewise, we have to do it iteratively until our. So I hope this is understood coding part. So about how we are going to take. Okay, I have Python code. Okay, so what I'm doing here is we are importing necessary libraries like addition, multiplications. Okay, we are importing scikit-learn, which is a publicly available data set. And this data set, there are three classes. So which is a categorical. Then we are using sklearn. We are importing our train test split. Okay, and from sklearn.tree processing, we are preparing our data for scaling and encoding. After that, we are using here a user-defined function we are defining. We are squeezing any numbers between 0 and 1. Since we are using sigmoid activation function, so we want all the values. I have written that formula earlier also, 1 upon 1 power e power minus z or minus x here. Okay, since we are taking x as an input. Okay, so here we want each and every value in the range of 0 and 1. And then we are using our function called as sigmoid derivative or sigmoid functions. Okay, which will help during our back propagations when we need to update the weights again. Okay, when we will need to update the weights again, we can use this user-defined function, which is our derivative of sigmoid functions. Okay. So likewise, what we will do, we are loading our data set now. We are loading our data set. With this variable name arrays, we can take any other variable name also. Here we are having x as an input, wherein there are what are the variables here? Sepal length, sepal width, petal width. These are all the variables present within this x. And what is our target variable? So target variable, we are doing our label encoding here. Okay, one hot encoding, sorry. We are doing one hot encoding here for making there is three classes here. Okay, so we are directly making into vector. So how the vectors will be formed? The vectors will be formed like if there are three classes, the vectors will be 1, 0, 0. Then it will be 0, 1, 0. Then it will be 0, 0, 1. Okay, so this is how the three vectors will be forming after this. Okay, so after that, we are standardizing our X so that all the features should be in the form of zeros and standard deviation. It should be 1. Oh, 1 minute. Yeah. So after that, what we are doing? Taking